Building upon our previous exploration of standalone quantum neural networks, we will now introduce our hybrid classical quantum architecture. In this demonstration, we feature a 5-qubit quantum neural network layer sandwiched between classical computing layers. We will utilize our hybrid execution wrapper to showcase both standard and sequential as well as batched training sessions, each conducted over 5 epochs on the HPC cluster. We begin with our standard initialization. We confirm our SSH configuration parameters and import the necessary libraries, including our HCQNN training wrapper and the local hybrid model architecture. By running a connection test, we want to verify that our wrapper has successfully authenticated with the HPC head node via native SSH mode. By running it, we verify that we established a secure link to our remote working directory. For our first example, we will execute a standard non-batch training session. First, we have to initialize the quantum execution wrapper, which is, in our case, the HCQNN training wrapper. We verify that it is connected to the HPC cluster, and we are now ready to submit our job. Notice here that for our parameters, we are passing our local HCQNN model.py and our data saved in .csv format. We also requested 2 cores for the execution and specified the number of epochs to be equal to 5. So by running this cell, we will start with the circuit submission. You can see in the console that the workload with a specific ID is changing from status pending to status running, and then, because it's a sequential approach, the next workload is being submitted. As you can see, the execution is now complete. The HPC cluster returns a comprehensive payload containing the optimized tensor weights for both the classical and the quantum layers, alongside the training loss for each of the 5 epochs. These results we instantiate a local copy of our model and parse the serialized state dictionary. As the prompt suggested, the optimized weights from the HPC cluster are successfully loaded into our local environment. By plotting the results, we can visualize the mean squared error loss convergence over the 5 epochs, and this way we can confirm that the hybrid model is actively learning and minimizing its error. So let's do this. For our next example, we will demonstrate the same training routine utilizing batch processing. In this configuration, we explicitly enable the batch training parameter and we define the batch size of 32. This allows the HPC nodes to process multiple data samples simultaneously per epoch, optimizing computational efficiency. We submit the batch workload to the cluster, and just as before, the interface handles the secure data transfer and execution polling. As we can see, the batch execution has finished successfully, returning a new set of optimized weights and loss metrics under a unique workload ID. So, as previously, we have to load a local model, and we of course need to load this new batch optimized state dictionary into our local model, ensuring our local weights reflect the latest remote computations. As the console output suggests, the weights loaded successfully. Finally, we will plot the batch training results. Observe in the convergence graph, the mean squared error steadily decreases across the 5 epochs, demonstrating the successful application of batch processing to our sandwiched classical quantum architecture.